Hi, I'm Paul from the Washington State University Department of Chemistry, and this quick help video is about limiting reactants and percent yield. So what you see on your screen is a typical limiting reactant problem. So we have a balanced equation for the combustion of butane. Butane is C4H10 right here, and that's just like the butane you would find in a disposable lighter or perhaps a camp stove. So it's a combustion reaction, meaning it reacts with oxygen, and the primary products of combustion of a hydrocarbon are always CO2 and water. So the equation is balanced, but the question asks us what happens if we react 50 grams, so 50 grams of butane with 75 grams of O2. And if we do that and recover 43.64 grams of CO2, we want to know the theoretical and percent yields. So let's start with the theoretical yield. So the theoretical yield is just that. So what do we calculate our yield of CO2 to be? And to make that calculation, we're going to take both of the reactants, that is butane and O2, and do a stoichiometry problem where we assume that it all gets reacted. So for C4H10 or butane, we start with 50 grams. So we have 50 grams of C4H10, and we have to convert that to moles. So anytime we're going to compare amounts of reactants and products, we have to go through moles. So the molar mass of C4H10, which we get by adding up the molar masses of all the atoms that make up the compound, that's 58.12. So that step would get us to moles, and now we have to use the coefficients in our balanced equation to relate moles of butane to moles of CO2. So we can see from the balanced equation that it takes 2 moles of C4H10 to create 8 moles of CO2. Right? That's directly from the balanced equation. And now our final step, we're going to come back out to grams. So 1 mole of CO2 weighs 44.01 grams. So if we do the math here and look at canceling units, all of those units go away except for the grams, and we would be left with 151.4 grams of CO2. So that would be the yield of CO2 if all 50 grams of butane reacted. Let's do the same for oxygen. So according to our problem, we've got 75 grams of O2, and 1 mole of O2 weighs 32.00 grams. Now again, at this point, we have to use the coefficients in the balanced equation, and we see that 13 moles of O2 is required to make 8 moles of CO2. And then just like before in this previous step, we're going to come back out to grams. So 44.01 grams is the molar mass of CO2. So it's a familiar pattern. Grams to moles back out to grams. And in this case, we get 63.48 grams of CO2. So both of these steps assume that we have used up all of the butane in this case and all of the O2 in the second case. And of course that's not going to be what really happens. So when we mix different amounts of reactants, one of those reactants is going to get used up before the other. So what we do is we choose the smaller amount. And so in this case, 63.48 grams is our theoretical yield of CO2. So what we're saying is that we're going to run out of O2 first. The 75 grams of O2 will react, create 63.48 grams of CO2, and then the reaction is done because there is no more oxygen available. So the limiting reactant would be the O2, the butane is the excess reactant, and 63.48 grams of CO2 is our theoretical yield. So what we've done so far is determine the theoretical yield. So our theoretical yield of CO2 was 63.48 grams. And now we want to find the percent yield. So the percent yield is really just a percentage of the theoretical yield that you actually make. So for instance, if you had a cookie recipe and the recipe says that this makes 3 dozen cookies, but when you did it, you only got 2 dozen cookies, your percent yield would be like 67%. So our theoretical yield is 63.48, but we can see here that's not what we actually got. The 43.64 grams is just a number we made up and said, suppose you did this experiment and you were able to recover 43.64 grams. So to get the percent yield, all we do is ask what percent of 63.48 does 43.64 represent. So the percent yield in this case, it's going to be the actual yield divided by the theoretical yield times 100. So it's 43.64 grams out of our theoretical 63.48 grams. And then we multiply by 100 to get it into percent units. And we end up with 68.75% as our percent yield. So that's how you do a limiting reactant problem to answer questions about the theoretical and the percent yields. And I hope that helped.